Welcome back, ladies and gentlemen. Mr. Eicher here to talk about a couple practice problems, making sure you understand what recursive functions are, how they differ from explicit functions, explicit formulas, and making sure you understand the notation. So let's get started in this section of our notes. Make sure you're taking some good notes, help yourself out. Using the explicit formula below, find the three terms of the sequence. So when you have an explicit formula, you can basically just plug in 1, figure out what that is, 2, second term, figure out what that is, and then 3. Plug 3 in, figure out what that is. So we'd have 3 times 1 plus 1. That's 4. So the first term is 4. The next term would be 7. And then the last term is, wait for it, 10. So our terms are 4, 7, and 10. First three terms. All right, let's look at B, our first term. So define when n is greater than or equal to 1. Our first term, we just plug 1 in. Our second term, we plug 2 in. And our third term, we plug 3 in. So plugging 1 in, we get 1 squared minus 1 minus 2. That would be 1 minus 1, 0. So our first term is negative 2. Our next term, you plug 2 in wherever there's an n. So that looks like it's 4 minus 2 is 2, minus 2 is 0. And then plugging in 3 wherever there's an n. Oops. So that would be 9 minus 3 is 6, 6 minus 4, 6 minus 2 is 4. So our sequence would be negative 2, 0, 4. Notice that these don't differ by the same amount. Between these two numbers, they differ by you're adding 2, but then these you're adding 4. So that's not going to be a linear function. But that was our first part, just using explicit formulas. The reason why I wanted to do that is to contrast it with these recursive formulas on the next example, which have a lot of notation that I want you to be familiar with. So let's look at those next. So in the previous two videos, we talked about recursive formulas. So recursive formulas have multiple parts. First, you're told what the starting point is. Your first term in this one is 10. And then on this next part, you're told to get the next term, or to get any nth term, you take the term before it, n minus 1, and then you add 6. Also important is to know when it's defined. This is defined for all n's greater than or equal to 2. So don't try to plug in anything other than 2 in. So we would say the first three terms, if we wanted the, notice also we have the notation, this f of n notation. Earlier we had a's, I think. But if we want our next three terms, we want our second term. Our second term would be our first term plus 6. Our first term was 10. Add 6 to that, and you get 16. To get our next term is our third term. Our third term would be our previous term right before it, and then add 6. Well, we just got 16 before, so 16 plus 6, our next term would be 22. And then finally, running out of space, I guess I'll have to write up here our last term, so our fourth term would be our term before it. Subtract 1 from 4, and then add 6. So our term before it was 22, we're adding 6 to that, so that looks like it's 28. So our terms, sorry, I ran out of space, our terms would be 16, 22, and 28. Those are our next three terms. Moving right along, let's look at the next example. This is a recursive formula, so we're told we're starting, our first term is 1, so our first term is 1. And to get any nth term, we're going to take 3 times this quantity. We're going to take 3 times our term before a sub n. And this is defined for n's greater than or equal to 2. So what would our second term be? Our second term would be 3 times the term before that. Well, our first term is defined right here. Our first term is 1, so our second term is 3 times 1, so we get 3. Okay. Our next term, our third term, we're going to take the term before it, or sorry, we're going to do 3 times the term before it, which is a sub 2, a of 2. Our second term is what we calculated, that was a 3, so we get 3 times 3, and that would be a 9. And then lastly, our fourth term, a of 4, would be our term before it, a of 3, times 3. Oops, I forgot to fit the 3 in there, times 3. So that would be 3 times the term before it, a of 3 is 9, so we'd get 27. So notice our sequence would be, we started with a 1, we went to a 3, and then to a 9, and then to a 27. This looks like an exponential function. These are perfect cubes. Or sorry, not perfect cubes. These are multiples of 3, 3, 9, 27. I guess they're perfect square? No, just multiples of 3. 3, 9, 27. So that's our sequence there. And if you'd like to pause, I recommend making sure you understand this. If you'd like to pause the video and try out this guy, notice you're starting at 0, and notice it's defined for 1s. But see if you could come up with the next 3 terms for that sequence. So we're starting our sequence at a of 0. I should probably write this. Since our notation's using subscripts, let me change this. It's probably already changed on your notes, but let me change mine. Alright, that's better. A sub 0. So our 0th term. Now it's a little confusing because a sub 0 is our starting point, so in a sense it is our first term. But it's a lot nicer whenever we start with a sub 1, because 1 is first. So a little confusing there. A sub 0 is our first term, but don't be too stressed out about that. So we have our next term in the sequence would be a sub 1. A sub 1 is defined this way. You're going to do 6 times the term before it, which is a sub 0. So this n minus 1 is, we're on 1. So 1 minus 1 is 0. And then minus 2. So our next term in the sequence would be 6 times where we're starting at 4 minus 2. So 24 minus 2 is 22. So that's our next term. And then we have a sub 2, our next term. We'd have 6 times a sub 1 minus 2. A sub 1 we just calculated as 22 minus 2. So that would be, let's see, 132, I think, minus 2. 132 minus 2 is 130. And then lastly, so we got 1, we got 2, we just need a third term. And I guess I'll write it over here. Our third term would be 6 times our second term minus 2. So our second term we just found was 130, so 6 times 130 minus 2, and that would equal 780 minus 2, so 778, I think. So our sequence that we would have, we start at 4, then the next 3 terms are 22, 130, and 778. So those are our next three terms after 4, our starting point. All right, let's finish up our last example. So in this last question it says match the recursive function above with the explicit function below. So let's see. If we did f of 1, we'd plug 1 into that, and that would give us 10 as our first term, and that looks like that would be matching. So this recursive formula is equivalent to this explicit formula. So maybe we could observe that this plus 6 as a recursive formula, you're adding 6 each time. That's your rate of change. When you write it as a linear function, that becomes your slope of your linear function. However, since this f of 1 isn't an f of 0, starting at 10, our y-intercept is not just 10. But if you plug 1 into this, as you can see, that's where that 10 comes from. Your first term is 10. So this linear function matches that first example. And then if we try to do f of 1 for this one, f of 1 would be 3 raised to the 1 minus 1. That's 3 to the 0, which is 1. So this looks like it's probably going to match. Let's just do one more just to make sure. F of 2, the second term, is going to be 3 to the 2 minus 1. So that's 3 to the first, which is 3. And that matches right here what we're expecting. So the thing I wanted to point out here, this recursive function matches this explicit function. So when you're multiplying in a recursive, see that 3 right there? That actually becomes the base of your exponential function. And then this example over here, I didn't write any explicit function for that. But I think that's the end of our video. There's just one more example problem to watch in this lesson. Thanks for watching. Have a great day.